Hello there.
Hi, Hari. So we will wait till 9:05 for students to join.
Okay, that's good. Okay, let me in the meantime share my screen. Okay. Okay, it's looking good, right?
Yeah, it's looking great.
Okay, cool. Okay, cool. So I'll just be back in a second.
Sure. All the students to mute yourself. Please mute yourself or please switch off your video. There is a lot of background noise. Students, please mute yourself. There is a lot of background noise. Students, can you please mute yourself? Thank you. So, good evening, everyone. So, I'm very happy to introduce Dr. Harikrishna Narasimhan, who will be delivering a guest lecture to my course on AI and ethics that is being run as a postgraduate elective at the Department of Computer Science and Engineering, IIT Kharagpur. So it's a big opportunity for us to learn from Hari what exactly the Google research team at Mountain View and other places are trying to do in order to uh, improve the TensorFlow stack to include various fairness constraints. So before I hand over to Hari, just a brief outline of Hari's profile. So he's currently a research scientist at the Google Mountain View in the AI team. And before this, he was a postdoctoral researcher at the Harvard, and before that, he finished his PhD from IIT Bangalore. So, and he has been doing some exciting research on optimization techniques and fairness issues in machine learning in the recent times. And he is one of the active members of the TensorFlow constraint optimization team. And we are all eagerly waiting to hear and learn from Hari. Thanks to Hari for giving time to us. I know it's an odd hour for you. It's a bit early in the morning. So thank you for getting up early and coming and joining us. So over to Hari.
Yeah, thanks, Professor Animesh, for the introduction. And I'm also very excited to talk to folks back in India and explain some of the work that we've been doing around fairness. So I've been at Google for a little over a year now, and I've been working with a team called Glassbox. Part of what we do is develop machine learning algorithms that are controllable, debuggable, explainable, and part of our research efforts goes into machine learning fairness, right? And this talk would basically focus on some of the recent work we have done around using constraint optimization for enforcing different fairness goals in machine learning. So I'm hoping to give you a flavor of the kind of fairness challenges of the kind of problems we work on using toy examples. Okay, so let's get started. And if you have questions, yeah, do ping on the chat box, and Professor would then interrupt me and sort of pass on your questions to me. Okay, let's get started. Uh, sorry. So all of you are familiar with the standard machine learning pipeline, right? So I'm just showing you a typical supervised machine learning pipeline, where you have some training data, some labeled training data, which is then fed to a machine learning algorithm. And then this algorithm solves some optimization problem internally and spits out a machine learning model for you. Right? And this is the standard pipeline that you study in a typical machine learning course at your university. But if you ask a practitioner, he would tell you that there's more to a machine learning pipeline than just this. Okay? So if you look at a standard machine learning pipeline, often the algorithms used are geared towards optimizing classification error. They are geared towards training models which have low classification error or which do a very good job of predicting, right, which have a high prediction accuracy. But in practice, there's more to training machine learning models than just minimizing the classification errors, right? Let's take an example. Say, let's take a toy example. Say you're a machine learning practitioner and you've been asked to create a recommendation engine. So you've been asked to, say, recommend restaurants to users. And you're asked to train a machine learning model which can recommend restaurants to users, right? So the input could be a search query on the type of, say, the food item I want to eat, the type of cuisine I'm interested in. So I might be interested in South Indian restaurants, and that might be my query. And the machine learning model needs to take this query and take a candidate restaurant and tell me if that candidate restaurant matches my query. This is a simple classification problem. And if you are asked to solve this problem, and if you are a practitioner, the first thing you would do is ask, who are my users, right? Who is this model serving? Because that's the key to sort of training a successful model. And it might turn out that your users are not just located in one country, but they are located in many countries across the globe. For example, you might have users in the US and you might have users in India. So a model which does a good job of recommending restaurants to users in the US may not actually do a great job of recommending restaurants to users in India. So in training models for such real world problems, there are a whole bunch of complexities that arises that a practitioner needs to face. Let's look at some of them, just sticking to this restaurant recommendation example. So if you have users across the globe, so one of the real world constraints that you might need to enforce is that your accuracy of your model is the same across different countries, that your model is not highly accurate in one country and does very poorly on a different population. So one of the real world requirement that might arise is that the accuracy of your model in India is similar to the accuracy of your model in the US. But a standard machine learning pipeline doesn't allow you to impose such constraints, right? A standard machine learning pipeline allows you to optimize for errors, but doesn't allow you to enforce such a requirement. This is one practical requirement that the practitioner faces. Here's another, right? One of the key to training a good machine learning model is coming up with a good training data set, collecting good training data. Now, often in practice, your training data may not be representative of the true test population, right? So if I want to recommend restaurants to people in the US and India, it might turn out that my training data set is overrepresented with restaurants in the US and is underrepresented with restaurants in India. So it may not, so training a model on this data set may not quite do very well on restaurants in different countries because the proportion of restaurants in your training data set may be different from the actual proportion of restaurants in the population. Sticking to the same example, suppose I'm interested in South Indian food, for example. The likelihood of me finding a South Indian restaurant in San Francisco is lower than the likelihood of me finding a South Indian restaurant in a city in India. So clearly the proportion of positive labels, in this case, whether a restaurant is South Indian, varies from country to country, but your training data set may not have the same proportion of positive labels as the actual test population. So one of the constraints you might have is for every country, you want to make sure that the percentage of positives predicted by your model matches the true fraction in the population. If you're looking at predicting if a restaurant is South Indian, that proportion may be much smaller in a city in the US compared to a city in India. So just for a toy example, assume that you want to constrain the positive prediction, the percentage of positive predictions from your model be 5% for a city in the US and 20% for a city in India. How do you impose such constraints on your model? This is just I'm presenting to you a second scenario where standard machine learning pipeline doesn't quite allow you to train models with these constraints. Now, remember, for simplicity, I've been looking at this problem of recommending restaurants as a classification problem. But what this problem really is a ranking problem, right? You really don't want to classify individual restaurants, but you rather want to rank restaurants based on the user's query. So a more natural way to solve this problem, and which is often used in practice, is to take a two-step approach. In fact, what one might actually end up using in practice is two different models. One model which first filters out good candidate restaurants, and a second model which then takes out the filtered restaurants and ranks them based on the user's query. So the first model does a retrieval. It's a filtering model. All it does is make sure that you filter out the bad restaurants which are not relevant to your query, and it gives a good pool of restaurants to a second model. The second model applies on the outputs of the first model and then ranks these restaurants, right? So unlike a typical machine learning setup, you have two models here, and one model's output impacts the second model. So how accurate the first model determines the accuracy of the first model determines how well the second model will perform. See, the first model ends up killing a lot of good restaurants. However good the second model is, you are going to do a bad job of recommending restaurants to users. So one of the key requirements of the first model is that it has a high true positive rate. What is the true positive rate? The fraction of positive relevant restaurants which end up being passed on by the first model. So you might want the first model to have a true positive rate of at least 70%, just for example, right? And in fact, this may not be as in it may not be enough to just guarantee the true positive rate is 70%. In fact, you might need to enforce this constraint for every country. You might need to say that for my users in India, the first model filters out at least 70% of good restaurants. My users in US, it does the same for US. In industry is that you train a model to replace an already existing model. Okay, so often in practice, what you end up doing is that you first train a model on a simpler model on whatever data is available. Then over course of time, train as you collect more data, train a better model and replace the existing model with a better model, and do this launch and iterate multiple times until as long as the model is active. Now, when I'm training a new model here, I need to remember that I'm replacing a previous model. So I can't train a new model which is arbitrarily different from an existing model. So one of the constraints that I need to be aware of is that the new model cannot make arbitrarily different predictions compared to the existing model. Even if the new model is very accurate, it can't be arbitrarily different from the previous model, because the user's experience depends on what model you use. So you don't want the user to have drastically different recommendations just because you decided to change the model you're using. So one of the constraints that you might want to impose is that the differences between the new model that you trained and the previous model that is already available in production is not too large. So random differences in predictions between the previous model and the new model says at most 2%. And again, this may be you may need to enforce this requirement for different countries. You might want to specifically look at India examples, and you want to make sure that new model is not different from the old model on Indian examples. Similarly for US and for all the major countries you are intending to serve. So this is just to give you a flavor of practical real world constraints that we end up having to satisfy by training a model. So clearly training a model is more than just optimizing for classification error. Uh, so stepping back a bit, so the way we look at a machine learning pipeline in our team is that, of course, you want to minimize classification error, but you also want to satisfy a bunch of policy or fairness goals. I call them fairness goals is because inherently what we end up doing is enforcing some notion of fairness in your model. You want to ensure that your model performs equally accurate in both India and the US. So you essentially want to be fair to users across the globe. So every constraint that I mentioned is some So how do you enforce such fairness goals in a standard machine learning pipeline? We view all these different fairness requirements as what we call as rate constraints. By a rate, all I'm referring to is the prediction rate of your model. I'm looking at the fraction of predictions that satisfy a certain property. For example, I might be interested in the positive prediction rate of your model, the fraction of positives predicted by a model. I might be interested in the accuracy rate of your model, the fraction of examples that your model made a true prediction on. I might be interested in the true positive rate of your model, the fraction of positive examples on which your model ended up predicting positive. So, so all the constraints that I've mentioned so far can be seen as constraints on rates of your model. So for example, one of the constraints we looked at was that the accuracy in India must be similar to the accuracy in the US, and that's a rate constraint because you're constraining the accuracy rate of the model. More formally put, what does this mean? You want to optimize for the classification error subject to a constraint on the accuracies in India and the US. And in particular, one possibility is that I constrain the accuracy in India to be at least 80% accuracy in the US. Just one candidate constraint I could impose. We then looked at a case where we also needed to constrain the positive prediction rate, the percentage of positives prediction from your model. And you wanted to constrain them specifically for different countries because the training data set may not match the true distribution in the test population. So we had explicit constraints saying the positive prediction rate in the US must match a certain threshold, in India must match a certain threshold. Now, this again can be enforced as constraints on the positive prediction rate on different slices of your data. So again, you want to minimize classification error, you might have a constraint on accuracy, you might have a constraint on positive prediction rate on different countries. Then we looked at a case where we had multiple models to train, and we needed to make sure that the first model filtered at least passed a large chunk of the good candidates to a second model, and therefore we needed to constrain the true positive rate of the model on different slices of the data. Again, super complicated constraint optimization problem where you want to minimize classification errors, but then you have a constraint on the accuracy rate, the positive prediction rate, the true positive rate, and you also have differences. You need to also constrain the differences in predictions across between the new model and old model across different countries. Now, of course, in reality, we don't enforce all these constraints at the same point, but just to give you a flavor of the kind of problems we encounter, I've listed out all the constraints in one optimization problem. And now let's look at how do you solve an optimization problem of this form. So this is just to give you a flavor of the kind of problems we look at. So in the rest of the talk, I would focus on two parts. The first part, I would look at some of the techniques we used for solving constraint optimization problems of the form I listed out. So these are constraint optimization problems to enforce fairness goals, specifically constraint optimization problems on rate constraints. So we look at some of the techniques that we have come up with. I'd like to give you a glimpse of the kind of techniques we use. And then the second part of the talk, I'd like to cover some of the practical aspects of solving this problem. And in particular, I'd like to highlight a recent library that we've been developing. It's the TensorFlow Constraint Optimization Library, which allows you to solve some of the constrained training problems that I've listed out. And I'll describe how the basic library interface, also present some experimental results that show that how the library works. So these are two main portions of the talk. At this point, let me pause a bit. So Professor Animesh, are there any questions so far? Or? Oh, I think you're muted, sorry.
No questions so far. Students, if you have any questions, can you please type it on the chat window so that I can pass it on to Hari? Any questions so far? No questions? So I think we can proceed.
Okay, cool. And feel free to interrupt me if you think something is not clear for your students and sort of.
Yeah, sure. I'll do that.
So having motivated the problem, let's look at the high level sort of algorithmic approach that we take. Okay, so let me set up some notations for this part of the talk. So for the first part of the talk, I'll set up some basic notations to explain what we end up doing. So again, as I told you, it's a typical supervised learning setup. So you have a training sample with features xi. Xi's are the feature vectors, and yi's are the labels. When we have 10 n different training data points, and we assume for simplicity that we're looking at a binary classification problem. So the labels are either +1 or -1. Now our goal is to learn a prediction model. Right? A prediction model, I shall denote a prediction model by f of x. You can think of this as a neural network model. It takes in a feature vector x and outputs a real value prediction. I will I'll denote the parameters of this model by theta. You can think of theta as the weights of your neural network. Right? So I have a prediction model which takes a vector x, outputs a real value prediction. Remember that we're looking at a binary classification problem. So what I would do is I would look at the output of this prediction model. If it's above 0, if it's positive, then I predict +1. If it's negative, I predict -1. So this is the basic prediction model. So f theta of x would be a prediction model. Okay, so this is a high level setup, and I'm sure you're super familiar with the setup of this form. So remember that we are interested in constraints on rate metrics. Right? Interested in constraining different rates on the prediction model. What do I mean by a rate? By rate, I'm just referring to just a loose term. It refers to the fraction of the training data on which an event occurs. Now, what are the events we are interested in? We might be interested in the positive prediction rate of your model, which is the probability that your model ends up predicting positive, that f of x is greater than 0. The probability that your model makes a positive prediction. That's a positive prediction rate. we might be interested in the accuracy of your model, right? The probability, the sign of the prediction matches the true label y. What's the probability on average? How many examples does your model make a correct prediction on? You might be interested in the true positive rate. What is the probability that your model makes a positive prediction given that an example has a positive true label? So among the positive examples, what's the fraction of examples on which your model makes a positive prediction? So is the true positive rate. So these are examples of different rates we might be interested in. Note that we're not only interested in the overall prediction rate, we are also interested in rates on different slices of your data, on different subsets, right? So for example, we might be interested in the positive prediction rate in the US, which is the fraction of so conditioned on an example belonging to or a user belonging to the US, what's the probability that your model makes a positive prediction for that user? We might be interested in the true positive rate, for example, specific to India. So conditioned on drawing a positive example from India, what's the probability that your model ends up making a positive prediction, right? So we are interested in prediction rates. We're interested in different rate metrics, and we're also interested in rate metrics computed on different slices of your data. Right? Now, because this is a Google specific example, I'm using countries as the different slices. Of course, in your course, you might have encountered other protected categories, right? For example, race and gender are common protected categories in some applications. Age is a protected category in some application. So you could, while the examples here focus on countries, you could look at other protected categories based on what application you've been working on. Okay, so these are different examples of rate metrics, right? So what we want to do is constrain these rate metrics. We want to set up a constraint optimization problem, right? Let's look at, for simplicity, a constraint training problem where you just have single constraint. So whatever I shall explain applies to multiple constraints and multiple protected groups. But then for simplicity, let's assume that we have a single constraint. This for a toy example. And assume that you want to optimize the classification loss, some classification loss on your training data set, subject to the constraint that the percentage of predicted positive from your model is above 80%. So what you want to do is train a model which optimizes some classification loss. For example, cross entropy is a common loss used in this. But you also have constraints that the percentage of predicted positives from your model needs to be greater than 80%. So how do you formally write a problem of this form? So here's the problem written in form and notation. So what we minimize is some average loss on your training data set. So f of xi is the prediction, yi is the label, and loss L is some standard loss. You can plug in whatever loss you like on the training data set. And I'm looking at the average loss, and I would like to minimize this average loss over theta. Theta are my model parameters. But then I have a constraint additionally that the positive prediction rate from my model is above 80%. And how does this constraint look? I'm looking at every data point xi and looking at whether my model makes a positive prediction. So I have this indicator asking if my model makes a positive prediction on xi, and I average out the indicator value across all my examples. And I want this averaged indicator value to be greater than 0.8. So I want an 80% positive prediction rate. Now this is the problem we want to solve. So what's the challenge in solving a problem of this form? Why can't I just throw in a standard stochastic gradient descent style algorithm to solve this problem? The main challenge in solving this problem is that the constraint is not differentiable in theta. If you look at the constraint, there is an indicator function which takes in the prediction from your model and it cuts it off at 0. So this indicator function is not continuous in theta. It's not differentiable in theta. So if I were to apply a stochastic gradient descent style method to solve this problem, I wouldn't be able to calculate gradients for theta. So that's a challenge. Right? Of course, there's an obvious solution to overcoming this challenge. What I could do is simply replace all these constraints with relaxations. I could just look at convex or continuous relaxations and replace these constraints with relaxations and solve the relaxed problem. So one obvious solution is replace the indicator with a relaxation. And the commonly used relaxation in machine learning is the hinge relaxation, for an example. So if you look at your indicator function, I have f of x on the x-axis, the prediction from your model. On the y-axis, I have how the indicator function looks. It's a step function. It cuts off at 0 and evaluates to 1 after 0 and evaluates to 0 before 0. Now I could smoothen out this indicator function and replace it with something like the hinge approximation. The hinge approximation is highlighted as a dashed red line here, and it's a convex approximation for this indicator function. So what I could do is take my constraint, replace all my indicators with the hinge approximation, and constrain the hinge approximation, right? So I could replace my original optimization problem it's something like this. Here, what I have is I optimize the average loss as before, but my constraint involves in relaxation now. So in my constraint, I replace the indicator with the hinge relaxation. And now I want to constrain the average hinge approximation to be greater than 0.8. But what's the problem in doing this? It's obvious solution. The problem is the constraint has changed. Now, earlier we had a constraint on the indicator. Now we have a constraint on a relaxation, and it's not entirely clear if optimizing if constraining the relaxation would actually satisfy the original constraint. So clearly the constraint has changed, and that could in fact be problematic in practice. So here is an example. Right? In many applications, particularly in the context of fairness, we might face problems in practice when we relax constraints. Relaxing constraints too aggressively can be problematic in practice. Right? And for example, so one of a common fairness constraint that is talked about in fair classification paper is this 80% rule. Now the 80% rule is a guideline given by the US federal government for hiring employees in your company. Right? And this is a guideline which makes sure that you do not discriminate and that you're being fair in your hiring process, that you hire from a diverse group of people. And this 80% rule, informally stated, and as many of you might have already encountered, states that the selection rate for a protected group must be at least 80% of the rate for the majority group or the advantaged group. So it basically says that that the rate at which I select people from a protected group, for my rate at which I hire people to my company from the protected group must be at least 80% the rate I hire people from the more advantaged group. Now, if you look at this, so this is a guideline given by the US federal government, right? Now, if a practitioner were to train a model to hire people in a company, just a hypothetical example, and the practitioner was asked to enforce that this constraint is satisfied, remember that 80% is not a number that a practitioner can change. When the guidelines say 80%, the guidelines actually mean 80%. So if I were to enforce a constraint that the selection rate for my model is 80%, I need to satisfy this constraint exactly. Right? I can't play around with this number and change this number just because I want my optimization to be convenient. So if I were to enforce the 80% rule, 80% is a threshold that a practitioner cannot change. So clearly, relaxing your constraints might have the effect of altering the constraint, and you may end up violating the an important requirement in law that you needed to enforce.
So Hari, there's a question from a student. So the question is, the way the optimization problem is defined, does y need to be +1 or -1? Or can it be extended to the regression setting?
That's a very good question. For simplicity in this talk, I've looked at binary classification. The library, the techniques that I described can be easily applied to regression problems. They can be applied to ranking problems, you're right, and also multi-class problems. So the techniques I described easily extend beyond binary classification. When we come to the library, I'll explain to you again with binary classification examples. But it's easy to also handle regression problems within our library, but might require a bit of work in doing that. But yes, regression, as far as the techniques go, they apply to regression problems as well. As far as the library goes, there are ways to set up constraints on regression problems. Okay, so moving on. Yes, so I was just mentioning in the slide that in reality, constraints have a real world meaning, and we may not be able to change the constraints arbitrarily. So relaxing the constraints arbitrarily may not be a great idea. So what we end up doing in the machine learning setup, G naught of theta would be a loss function, theta would be a model parameters, and GI of theta would be the different rate constraints that I specified. So GI of theta, you can think of as the positive prediction rate or the true positive rate or the accuracy rate on different slices of your data. Now, G naught of the problem here is GI of theta is not differentiable in theta. That's what we need to handle. The first step in solving this problem we formulate the Lagrangian for this problem. What does a Lagrangian do? I'm sure a lot of you have encountered the use of Lagrangians to solve constraint optimization problems as a part of optimization courses you have done, and also as a part of the machine learning course you have done. So a Lagrangian basically takes a constraint optimization problem and converts it into an unconstrained problem. It introduces penalty weights for different constraints. These are called the Lagrange multipliers. I denote them by lambda i's here. So it takes the constraints, lifts them, and makes them a part of the objective, and weights them by the Lagrange multipliers lambda. So now the optimization is over both theta, model parameters, and also lambda, which are the newly introduced Lagrange multipliers. Now what I've written out here is the standard Lagrangian for this problem. Right? So that's I've converted an unconstrained problem to a constrained problem where I weighted the constraints by the Lagrange multipliers. Now note that the Lagrangian is still not differentiable in theta because gi of theta is not continuous in theta. So still we have the problem of the Lagrangian being non-differentiable in theta. But one nice thing here is, while the Lagrangian is not differentiable in theta, it's differentiable in lambda. If you look at the lambda here, the Lagrangian is linear in lambda. So I can differentiate lambda. If I want to optimize lambda, I can do that without any relaxation. It's only when I need to optimize theta that I have a problem. So what we do is to first formulate the Lagrangian for this problem. We also formulate the relaxed Lagrangian for this problem. That we take the original Lagrangian and replace the constraints with relaxations. So for every constraint gi tilde is what I use to refer to the relaxation. So you can think of gi as the positive, as some positive prediction rate, and gi tilde as a hinge relaxation for that rate. So the G1 formulate the relaxed Lagrangian where gi's are replaced with gi tilde. Now what we do is use this observation that for theta I need relaxations, for lambda I don't need relaxation because my first Lagrangian was linear in lambda and differentiable in lambda. So the idea that we use is that we update both theta and lambda simultaneously. We minimize the Lagrangian over theta, but for minimizing theta, we use the relaxed Lagrangian. So we optimize the relaxed Lagrangian with respect to theta, and we optimize the original Lagrangian, the true Lagrangian with respect to lambda. We maximize the true Lagrangian with respect to lambda, and we optimize the relaxed Lagrangian with respect to theta. So you can think of this as two alternating updates. We have a gradient update in theta. For that, we use relaxations. Then we have a gradient update at lambda, for which we use the true metric, the original metrics. Right? So by using the selective relaxation, we are able to finally guarantee, and often we see in practice that we are able to satisfy the constraints more closely than using relaxations globally. So more intuitively, what we are doing here is that we use relaxations only when we need gradients for theta. We use the original rates when calculating the Lagrange multipliers, when optimizing the Lagrange multipliers. Remember that the Lagrange multipliers assign penalty weights to the different constraints. So while assigning penalty weights to the different constraints, by penalizing the constraints, we use the true constraints, the true rates. But only when optimizing the Lagrangian do we use relaxation. So when optimizing the constraints, we use relaxations. While computing the penalty weights, the Lagrange multipliers on the constraints, we use the true original rates. And by doing the selective relaxation, we are thus able to stay true to the constraints. And this is where our approach differs from prior methods. Now, what I presented is just a glimpse of what we do, right? I've oversimplified things so it's easy to present in the classroom. If you want to know more about our algorithmic approaches, please take a look at a recent JMLR paper that my team has put out. Now, this paper has all the algorithmic details. In fact, the actual algorithm is slightly more complicated than what I presented. And there are also a very nice theoretical analysis of these algorithms. In fact, the analysis is based on game theory and two-player games. So you might want to take a look, in case this is something you're interested in knowing more about, please take a look at the JMLR paper. I was not personally involved in the first piece of work, but I've been involved subsequently in follow-up works where we have extended this approach to handle more complicated evaluation metrics. Often in practice, people are interested in the true positive rate and the positive prediction rate of a model, but often practitioners also care about other metrics like AUC or precision. And we have a subsequent paper where we show how the same technique can be applied to optimize more complicated evaluation metrics like AUC. Okay, so this gives a high-level sort of overview of the core algorithmic approach that we take. Now, having gone through the high-level algorithmic approach, I think let me spend some time describing to you how the library functions. Right? Let me describe the key components of the library. So far I've told you what the high-level constraint optimization problem is. I've told you how we end up solving it, given you a high-level overview. Now I'd still like to describe how our library ends up setting up this optimization problem, how it provides a flexible interface to set up such optimization problems in TensorFlow. At this point, let me stop again. So I'm halfway through what I wanted to talk about. Are there any specific questions from the students? I'll be happy to pause a bit and reply those, answer those questions.
So any questions from the students? Students, you have any questions? So, Hari, are you taking questions also from faculties?
Yeah, please.
So, I have a small clarification. Sometimes practitioners are also interested in misclassification rates rather than
Yes.
classification rates. So, is your model generic to accommodate those kind of rates also?
No, when you say misclassification rates, are you referring to accuracy versus error? As in, you're saying you might want to maximize something rather than
Yeah,
minimize
so
something?
for instance, the false positive rate or the false negative rate.
Yes. So that's a good question. Yeah. So we are, so whatever I presented, just this is a specific example, right? It's so actual libraries goes much beyond just the true positive rate. So so even the negatives of these rates can also be easily set up. In fact, we allow, as I point out in the library, in fact, you can take combinations of all these and write out your own mathematical expression and say, oh, I want to optimize alpha times the true positive rate plus beta times the true negative rate, or beta times the false positive rate, and you can set up such constraints. So the library is very flexible and allows you to come up with combinations of different rates and set them up as constraints in your optimization problem. Okay. Okay.
So
I
there
see
is
that.
one more question
Yeah.
from the students. So the question is, do we encounter theoretical bounds of the desired fairness goals with respect to the data?
Yeah, that's also a good question, right? So I think the question is, as in I've outlined a high-level algorithmic approach, and I'm like, oh, what we do is the selective relaxation. So for one part of the optimization, we use the two rates. One part we use relaxations. Question is, does this have theoretical guarantees in practice, right? The answer is yes and no. So our paper goes into great lengths into deriving theoretical bounds, right? But then the theoretical bounds are not completely satisfactory because we do end up using relaxation. So if you were to solve the original problem without any relaxations versus if you were to solve the problem with relaxation, obviously there is going to be a gap, right? Because when you use relaxations anywhere in your optimization, you are doing something approximately. So you're not going to be able to solve the original optimization problem exactly, right? So the final theoretical guarantees, what they state is that you you do satisfy the original constraints, but then they under certain assumptions. I would like to go into what the theoretical assumptions are. The answer is yes, we do have theoretical guarantees. They work under strong assumptions, but in practice, we find that this approach works better than just simply sort of relaxing your constraints globally with relaxations. Using the selective relaxation works better in practice than global relaxations. In theory, yes, we do have theoretical results, but under some strong assumptions. Yeah. So thanks for the question. Okay, so let's now move on to the library, right? And I think this is the more practical aspect of the talk, and this might be something that interests a lot of students who actually want to end up solving some of these constraint optimization problems for their projects in the course. So yeah, so what is this library? It's the TensorFlow Constraint Optimization Library that our team has been developing at Google. And it's an open source library. So I have a link to the GitHub repository. So this library, we abbreviate it as TFCO. It provides a flexible interface for setting up constraint training problems in TensorFlow, and particularly looks at constraints based on rates, different positive and negative prediction rates. This is a TensorFlow based library. We support TensorFlow 1.14, and later on we support both graph and eager mode within TensorFlow. So let me quickly go over what are the high level set of steps in setting up a constraint optimization problem with this library. So the overall workflow of the library has three main high-level steps. The first step is to create a context object. Right? The context object basically tells the library which slice of the data you're interested in. Example, if you're interested in examples from US and India, if you're interested in examples belonging to two different races, this is where you specify to the library that these are the different slices of the data I'm interested in. So I first create a context object, and this context object will be told which slices of your data you're interested in. Next, you then say what metrics you're interested in. So you need to specify what rates you're interested in. Are you interested in the true positive rate, the false positive rate, the accuracy rate on specific slices of your data? So having identified the slices in the first step, you say what rates you're interested in. Having identified the rates, you then set up the constraint optimization problem. You say, this is what I want to minimize, and these are my list of constraints. And in fact, one of the nice things about this library is that you can specify the constraints using simple mathematical expressions. Once you say, I'm interested in true positive rate, the false positive rate, you can combine all of them using simple mathematical expressions and specify them as constraints. Let's look at a simple example to sort of explain how all three steps work. Say you're interested in a simple binary classification problem. You have a data set with binary labels. Assume for simplicity that you're interested in two protected classes, two protected groups. Now, of course, the library can handle any number of protected groups and any number of constraints. So you have, let's say that you're interested in red and blue examples. Just to keep it neutral, you have one group which is red, one group which is blue. And assume that you have features which separate out these examples in the data. So you have binary Boolean features, indicator features. You have a feature called isRedIndex, which has a value of 1 for all the red examples. And you have a feature called isBlueIndex, which has a value of 1 for all the blue examples. So you use these features to identify that's the slice of the data you're interested in. And let's say we are interested in the simple optimization problem. We want to minimize error rate subject to the true positive rate for the red examples being greater than 0.9 times the true positive rate for the blue examples. It's a simple constraint optimization problem. Okay, now let's see how to set up this optimization problem. So the first step is building the context. So these are contextual Python objects that a library creates. So you first need to create a context for the overall data set. You need to say what my predictions are and what my labels are. So model of examples here is basically the logics that your model outputs. So these are your predictions. So this model might be a neural network model. For example, you might be using models in keras. So you might have a neural network model. You apply this neural network model to examples in your data set, and then you get out a prediction tensor. Then you have another tensor which contains the labels. So your library basically takes, to create a context, you specify the predictions, the logics, and your labels. Then what you do is, this is the overall context. Then you need to create a context for every subset you're interested in. If you're interested in the red examples, then you specifically say that for all examples for which this particular feature is red index is greater than 0, those are the subsets I'm interested in. I create a separate context for that subset. Then I subset the examples for which the blue index is greater than 0, and I create a context for the blue examples. So this gives you the context. The second step is specifying what rates I'm interested in. For that simple optimization problem I listed in the previous slide, you might be interested in the error rate on the overall data set. So you say error rate of the overall context. Then you say I'm interested in the true positive rate. So TFCO, the true positive rate for the red examples. So you specify the red context. Then you say you're interested in the true positive rate for the blue examples. So you say true positive rate of blue context. So you then specify the 3 different rates you are interested in. Next, what you do is now specify your optimization problem. You need to say that I want to optimize error rate, but then I have constraints on the true positive rate on the red examples, the true positive rate on the blue examples. This is how I specify a constraint optimization problem. I say TFCO rate minimization problem. This will create the constraint minimization problem for me. Just focus on the first line here. What I specify here is what the objective is. So the first argument here is the objective, which is the error rate. So in the previous step, I created the error rate object. So I pass that as my objective. Then I specify my constraints using a list. So I need to specify a list of constraints. So I create a list. And in this case, there's only one constraint. So there's only one entry in the list. And this constraint basically tells the true positive rate for the red object. The red examples are greater than 0.9 times the true positive rate for the blue examples. And you can create, as I told you, you can look at more than 2 slices. You can look at multiple protected groups. And here in this list, you could add multiple constraints. And all you need to do is specify these constraints using plain mathematical expressions. Okay, and then what you do in the final step is we provide a custom optimizer. So you can use that optimizer to to generate a operator for the optimization. You get a train op using the optimizer we have. Then you go and do your standard TensorFlow training where where you use your data to optimize or to minimize using this train op. Okay, so this is a high-level overview of how you end up setting a constraint optimization problem. If there are any questions, do ping me. I'll answer you immediately. For the time being, let's then move on to a particular specific application so that you get a flavor of how this works in practice. So I'm going to look at a tutorial that we have put out. We have several tutorials up on our GitHub repository. So one specific tutorial that I found interesting is this wiki toxicity tutorial. So this uses, so in this tutorial, we sort of showcase how TFCO can be used to enforce fairness goals for a specific text classification task. So for the rest of the talk, let me go over a bit of the experimental results we have here to give you a flavor of how this library works in practice. So the application we're going to look at is the following. So we have comments posted on wiki talk pages by users. These are discussion comments. And we'd like to check if a comment contains toxic content, right? By toxic content, I mean that the comment contains rude, disrespectful, or unreasonable content. Now, so the goal here is to classify these textual comments on wiki talk pages as being toxic or not toxic. Now, the data set we have is a publicly available data set. This was put out by a team within Google. They're part of the Conversation AI project. So the data set contains around 1 million comments, more than 1 million comments from wiki talk pages. And these are manually labeled by human raters as either being toxic or non-toxic. In fact, there was a recent Kaggle competition hosted, which used this data set, right, for the same task of predicting toxicity of comments. So remember, these comments are textual comments, right? They have text comments. The label is here, output is a binary label. Is the comment toxic or not? Now, so the goal is to predict toxicity for individual comments. The challenge, however, is that the data set is imbalanced, meaning that certain categories of comments have a higher proportion of toxic comments, right? In particular, if you look at the category of sexuality, so if you have comments which talk about sexuality, you find that this category of comments have a higher proportion of toxic comments. And this could be problematic when you do training, because so toxic comments within some categories tend to be overrepresented in the data set. So a model may end up learning a bias. So let's look at what happens when you train a model without any constraints, right? When you just do your plain, training with some standard loss like the cross entropy loss. Let's see what happens. Now I'm pulling out numbers from the conversational AI team's GitHub repo. So what they do is they train an unconstrained CNN model, okay? And it turns out that this model has some unintended bias. And what do I mean by bias here? It turns out that this model ends up having a lot of false positives for some group of comments, for some identity terms. So I list out a bunch of comments and I'll showcase what score this model gives. So I'm talking about a model which is trained without any constraints. So here are 3 sentences, right? These are 3 comments. So the first one says, I'm a proud, tall person. And the model gives a toxicity score of 0.18. So the toxicity score is the probability of the comment being toxic. It's a value between 0 and 1. So it gives a score of 0.18. The second comment says, I'm a proud lesbian person. And you have 0.51 as the toxicity rate. The third comment says, I'm a proud gay person. It has a 0.69. But as you can see, these comments are neutral comments, right? There's nothing toxic particularly about these comments. But for some reason, the model misunderstands all these 3 comments as being toxic. It gives, in fact, for the second and third comment, the toxicity score is greater than 0.5, which means the model is certain that these are toxic comments when they actually are not toxic. So what is the reason? The reason is that that comments pertaining to sexuality, comments which contain terms like gay or lesbian, tend to have a large number of toxic comments. Large number of comments labeled as toxic. So the model, when it's trained without any constraints, just ends up memorizing that these words like gay or lesbian, or words pertaining to sexuality, are indicators of toxicity and automatically classifies those comments as being toxic. So in other words, the model happens to have a lot of false positives. It falsely classifies a large portion of genuine comments as toxic. And this happens particularly for specific categories of comments. So what we did was we tried to first replicate the results they had with this data set. So we, on our end, we trained a CNN model without any constraints, and we looked at 4 groups of comments. We looked at comments which contain some term related to sexuality. We looked at comments containing some term related to gender identity. We looked at comments containing some term related to religion. We looked at comments containing some term related to race. So we have 4 categories of comments, right? Whenever a comment contains a term related to religion, for example, if it contains a particular religion in it, then we say it belongs to the religion category. And likewise for the other 4 categories, other 3 categories. And this is the results that we see. So we trained the unconstrained CNN model, and this is what we ended up getting. So in this bar chart, I've basically shown the false positive rate of the model for different categories of comments. Overall is the overall false positive rate. Then you have false positive rate on 4 different categories. As you can see, the overall false positive rate is less than 2%. Whereas the false positive rate for sexuality related comments is as high as 8%, more than 8%, which means specifically for that particular category of comments, there are a large number of false positives. A large number of genuine comments are classified as being toxic, which could be problematic. Now, remember that the overall accuracy of the model is 95.8%, which is a reasonably okay accuracy. But then the false positive rates are highly skewed. For one particular category, there's a huge false positive rate. For all others, the false positive rate is reasonably low. So what we ended up doing is seeing if we can use TFCO to correct for some of these biases. So we use TFCO to solve the following constrained optimization problem. So here the goal was to minimize error rate, right? Which is what the unconstrained model did. But then we had specific constraints saying false positive rate for sexuality is less than 2%. False positive rate for each of the other 3 categories is less than 2%. Remember, the overall false positive rate was less than 2%. So the natural constraint we imposed was the false positive rate for each of the different categories that we care about. The data set has multiple categories, but these were 4 categories we were particularly interested in. So for these 4 categories of comments, specifically, we wanted the false positive rate to be under 2%. This is the optimization problem we solved. So let's see what happens. So this is what we finally get. On the left-hand side, I've again shown you what we got with the unconstrained model. On the right-hand side, I've shown you what we get with the constrained model. The constrained model is also a CNN model. Again, I've shown the false positive rates. As you can see, that overall, there's a reduction in the false positive rate, and particularly for sexuality-related comments. Earlier, we had up to 8% or more than 8%. Now it's reduced considerably, and there's a 70% reduction in the false positive rate for sexuality-related comments. So clearly, this is a significant reduction in the false positive rate. As you can see, the second model, which is trained with constraints, can be seen to be more fair because it has a lower false positive rates for all categories, right? And particularly for sexuality-related comments, there's a much lower false positive rate. If you look at the overall accuracy, which in the title of both these charts, I reported the accuracy. The accuracy reduces from 95.8% to 95.1%. There's a slight dip in accuracy, but then the dip in accuracy is much small compared to the reduction we get in the false positive rate. So clearly, the second model, though there's a slight reduction in accuracy, that's much better on the false positive rates. Now, one question you might have is that when we solve the constraint optimization problem, we had constrained the false positive rates to be under 2%. But then as you can see here, the false positive rate for sexuality is not under 2%, slightly over 2.5%. The reason for that is that the constraint optimization problem that we solved was on the training data set. So the numbers I'm reporting here are on the test data set. And that's why you see a small gap between the constraint we enforced and the constraint that eventually got satisfied. So let's see, there's a chat. What is the distribution of these categories on the data set? So that's a fantastic question. So by categories, I think you're sort of referring to the 4 categories of toxic comments. You see that almost more than 30% of comments in that category end up being toxic. So there is a difference in distribution. So the overall distribution of toxic comments is like 10% toxic and 90% not toxic. Whereas for sexuality related groups, it turns out the toxic comments are overrepresented, meaning that you have a larger proportion of toxic comments for sexuality related groups. I don't quite recollect the numbers for other groups. I can pull them out and send them to you, or please feel free to go and look at the tutorial. The tutorial has all the details. Now let me, so I guess there are other questions as well. Let me quickly go over the other questions.
So the question is, can one sentence belong to multiple classes as well, like sexuality and race?
That's a very good question. And the answer is yes. But then from what I remember looking at the data set, and again, I would urge you guys to go into the tutorial, download the data and play around with it. And as I said, there's a Kaggle competition. So you can go there and sort of play around with the data set there, where the data set is much larger. So the answer is yes, there is overlap. But as far as I can remember, the overlap was not significant. Right? Though there were comments which belong to both sexuality and race. And in this particular example, I don't look at those intersectional groups, though it's yeah. So, but from what I recollect, those groups were smaller in size. But in practice, this raises a very important point that in practice, you are quite often we find that though we constrain the individual groups to have a nice false positive rate, when you look at the intersectional groups. So if you look at, for example, comments which belong to a particular race and belong to a particular sexuality, then you find that the false positive rate is not that great. So constraining the individual groups may not have the effect of constraining some of these intersectional groups. So that's a great point. Yes, there is overlap. The overlap is not too significant, but in practice, that's an important concern that we should also care about some of the intersectional groups. Can we extend these ideas to unsupervised setting also? Now, when you talk about unsupervised learning, right? So everything here is supervised because you problems. But the library can be used to also handle unconstrained settings. It might need some amount of extra work in setting up the library to handle unconstrained problems. But then you need to be clear about what is the objective when optimizing. Because I don't have labels, I need to be clear what objective I want to optimize. So you'll have to write out that objective yourself in TensorFlow and then plug it into the library as the objective. So there's a way that the library allows you to specify your own custom objectives and then wrap them around into the library using the library helpers. So you can do that. So, but you'll have to write out the objective yourself. For example, here when I say error rate, the library takes care of computing the error rate, computing and relaxation to the error rate if needed. But if you are going to use your own objectives, like if it's a clustering problem, the library doesn't have built-in helpers to set up objectives for clustering problems. So you will have to say, what is the distance objective I'm going to optimize? And when it comes to fairness constraints, you'll have to say, how do you specify your fairness constraints? And there might be an easy way to translate whatever problem description you have into constraints or into rate constraints that the library can set up for you. So yes, it depends on what exact problem you have, what exact object you have, what exact constraints you have. The ideas in general can be extended to unsupervised setting. The library does support more general constraint optimization problems, but it might require a bit more work and might require you to explicitly specify some of the constraints yourself, and you may not have the library do it for you. And finally, to be honest, I'm not too familiar with the literature on fairness and fairness. So let me see. So we can use the library for solving any constraint optimization problem. Yes, the answer is yes. You can use the library to solve any constraint optimization problem, but it will require a little more work for you to specify what the objective and constraints are. Yes, the answer is yes. And I would urge you to go and look at the library GitHub repository where we have the first basic tutorial that we have also tells you how to set up your own constraint optimization problem. But coming back to the problem of fair clustering, I'm not entirely familiar with the literature, though I should be. So yes, so yes, I'm not entirely familiar with what type of fairness constraints people care about in the clustering literature. So I'll have to look at that in a bit more of detail before being able to give you a more concrete answer. Is the CNN model trained using simple glove embeddings? I mean, does the input embedding affect the performance? Has it been tested with different ablation of embedding types? Yes, the CNN model is trained with simple glove embeddings. That's a good point you make. But the CNN model also has the option of training its own, as in making the embedding a parameterized layer and having the embedding layer also be trained as a part of the overall training. We didn't do that because the focus in this particular tutorial was not so much on getting the CNN model to do a terrific job, but rather sort of looking at standard CNN models and sort of pointing out that, see, there could be biases, and you need, and the question is not about the modeling per se, right? You could have a fantastic model, but because the way you set up your objective and constraints, your model may end up learning some inherent bias, right? And you're right, maybe sometimes you could overcome that by just improving your model, but often it's not so much about the modeling being not flexible enough, but it's more about the objective we're optimizing. So the focus here is more on the loss function you're optimizing, the constraints you're imposing. And the high level message is that rather than breaking your head over how do I change my CNN model, how do I change the type of embedding to do better on this particular data set, maybe what you should be focusing on is specifying the right set of constraints so that the constraints take care of avoiding such biases. But these are fantastic questions. Thanks so much. So feel free to mention other questions. So I think I've come pretty much to the end of the talk, and of course we are running out of time as well. So let me quickly summarize what we have covered so far. Feel free to post more questions. So we started out by sort of motivating some of the constraint optimization problems we encounter, that a practitioner may encounter, and I gave you a flavor of the kind of problems we encounter at Google. I then sort of we specified some high-level algorithmic technique based on selective relaxation to solve these constraint optimization problems. And there the high-level message was, don't relax your constraints globally because that might be problematic in practice. In fact, constraints have a real-world meaning, and maybe overcome some of the biases that training a CNN model without constraints may end up learning. Okay, so this brings me to the end of the talk. So just one slide on throwing at you all the relevant information. So this is a link to the GitHub repository. Feel free to search for TensorFlow constraint optimization. This link would pop up. We have two high-level tutorials. There are a number of tutorials, but if you really want, if you're super interested in, say, neural network training, then these are the two tutorials you should be looking at. I would urge you to first look at the Celibae example. This is the celebrity data set, celebrity face detection data set. And that has a simple example. Then the wiki toxicity is slightly more complicated, but then I'm sure a lot of you are already familiar with neural networks. And so it might be quite elementary for you. Then there are two papers that you might want to look at. There are there's a whole host of papers we published over the years, but then these are two high-level papers you might want to look at. Let me at this point acknowledge some of the TFCO authors who have contributed over the years to this project. These include both authors within Google. Andrew Carter, for example, has been spearheading the library. He literally wrote up the library from scratch, and he has been spearheading a lot of this effort. Maya Gupta is my manager. And then you have a whole bunch of folks from both within Google and from academia who have contributed to this project. The slides particularly are adapted from slides that Maya Gupta, Serena Wang, and Andy Carter had used in previous talks. So at this point, let me thank them for lending some of their slides to me. So, and my name is Harikrishna Narasimhan. I work at Google Mountain View, and this is my email ID. So if you want to reach out with questions, feel free to reach out to me. So my email ID is hnarasimhan@google.com. Okay, so I think this brings me to the end of the talk, and yeah, I think if you have further questions, I'll be happy to answer them.
So, Hari, I have a question.
Yes.
So, in addition to these fairness goals, currently there is a lot of interest in generating explanations or interpretations about the models. So, are you thinking of adding to the pipeline of TFCO some interpretations or some explanations? Like, for instance, you did some constraints, you put some constraints, and then again, it's a black box. Like how these constraints work, what actually comes out of the black box, why was this change? So are these kind of questions into the recent or future perspective of the Google team? Or?
Yeah. So see, different teams in Google's has different priorities, right? So this was a specific project where the goal was to solve constraint optimization problems seamlessly in TensorFlow. So you're right, explanations are very important. But then the way we do it, we do things in a modular fashion. So this is one module, right? So TensorFlow constraint optimization builds on the existing TF stack so that with seamlessly someone can just specify constraint optimization problem and solve the problem as they would do with the standard TF training. Explanations, I think are not sort of specific to fairness problems per se, right? That's a separate effort by itself, right? Coming up with explanations of models. So see, since this is well integrated with TensorFlow, you could do training with TFCO, you could do training without TFCO, and then apply whatever tool you have for generating explanations from TF models. And you could apply to both of them, and you could use that, for example, to see what exactly what exactly changed with constraint optimization. You're right that it is a black box technique, but then the goal here was not to make things more transparent. What the goal here was to allow users to easily specify a constraint optimization problem and overcome some of the biases. Now, within Google, there are other teams which have been focusing on, say, diagnosing bias in models. And there's a team which works on fairness indicators, which is a tool, I think, which is also publicly available, which allows you to diagnose biases within models. They don't generate explanations per se, but they allow you to slice your data in different ways and sort of see if your model is biased to a certain slice of your data set. Then there's a what if tool, which Google has released, which I think tries to do things like sort of generate, as in, figure out why exactly a particular outcome is generated by the model. And again, we can look a bit more into these tools. And I'm sure there are other tools within Google which allow you to do that. My team in particular has other projects, not particularly related to constraint optimization, on explainable machine learning. The focus there is not on generating explanations, but to design machine learning models which are explainable inherently. So rather than using a neural network and training it and then breaking your head about why your neural network made a particular prediction, why not re-architect your model in a way that it automatically is explainable? And that's an effort that, at a very high level, that's what we do. And that's an effort that's going on by other members of my team. I can talk more about it at some other point in time. At a high level, yeah. So, and I can also try to pull out some tools that Google has for generating explanations so that if that's useful to you, I can forward those as well.
Thank you. So any other questions, students? We'll wait for 2 minutes.
Okay.
If there are no other questions, we will stop. Okay, I guess there are no more questions. Thank you very much, Hari. So it was a wonderful lecture, and I hope the students have benefited. At least I myself have benefited a lot. And I hope the students have equally benefited. And if there are some other queries from the students, I would request them to directly point them to you, or they can write to me, which I can point back to you. Okay. Thank you very much. Have a good day.
You too. Thank you. See you. Good night. Bye. See you.